Cool. Okay, so quick rundown. Well, I'll leave the introductions for later. I've got a fun little story to start with. So this is push button receive location. I'm going to cover a few little things about radio navigation systems, but rather than do the obvious GPS, I'm going to talk about land-based radio navigation. So set the scene. Congratulations, you lost. You had a lot of fun at campground last night, but you also drank rather a lot of Bucky. You've woken up in the middle of a field. You have a map, a radio receiver, and a compass. Somehow you found a traffic cone, but that's not going to be relevant to the story. That's just a happy little side effect. You've no idea where you are. None of the scenery looks familiar. And somehow your mobile phone battery is flat, so you ain't got a GPS receiver. Your quest, figure out where you are and get back to campground. And yeah, your phone's flat. You don't have a GPS receiver. Nice try. So there are a couple of ways you can do this. There's the obvious kind of look for landmarks. We're going to assume you can't find any landmarks. You're in a field and that's all you can see. But we're going to use that little radio as a way to find out where you are. Helpfully, your map has a list of radio transmitters nearby, their frequencies and where they actually are. So you know where these transmitters are and you have a receiver. You can and you can figure out where you are based on that. So this process is called triangulation. Effectively, you work out your angle from your position to the transmitter. Your receiver is helpfully directional. There's a couple of ways to do that. First of all, obviously, directional antenna. They're usually quite large. Maybe you've happened to fashion one out of things you found in the field. That's not outside the realms of possibility. They are, after all, just a little bit of wire and a stick. I can hear the amateur radio operators in the audience preparing to throw things at me for that comment. But curiously, you can actually make one out of a tape measure and a stick. So what you do is you use your directional receiver to work out your angle to the transmitter. Draw a line from the transmitter to at that angle on the map. Do the same for a couple of transmitters, and where the lines overlap on your map is a fair approximation of where you are. The more transmitters you measure from, the lower the error drops. So this is done quite regularly for radio orienteering or ARDF, amateur radio direction finding. The common form those take is actually fox hunting, which is where you have a transmitter sending a beacon signal, which you look out for and receive. Your directional antenna will obviously pick up a stronger signal in the direction of the transmitter when it's pointed at the transmitter. So you just follow the line effectively. Eventually you get to a point where the signal is so strong and so close by that the antenna is just picking up a full signal in nearly every direction. And at that point you're down to visual. You're looking for the thing. Rather than using the radio, you can use attenuators to reduce the signal strength, but at that point the directionality of the antenna isn't going to be very good. If you don't happen to have a directional antenna, there's a trick you can use called body blocking, which is where you literally move around. You keep the radio close to your body, leave it set on receive, keep an eye on the signal strength meter, and just move your body around in different sort of angles and look for the null, look for the weakest point and the strongest point of the signal. That will again give you an idea with the compass of what your angle is to the transmitter. Draw a line on the map, repeat. Given our sort of scenario, this is more likely what you would do in that situation. But to be quite frank, if you've got a ham radio transmitter, a Baofeng, the easiest way of doing it is to ask other people to DF you, to direction find your signal and transmit. Hey, it was a fun little example. And somehow you've ended up in Cumbria. I have a confession to make. This is actually the part of the transmitter map for the next section. I was too lazy to do a new example. So you can see from the diagram there, you have the three transmitters, 11, 12, and 15. You've figured out your angle to those transmitters. You've drawn the lines and they intersect somewhere in Cumbria. So that's a roundabout way of setting the scene and showing you what the utility of this kind of thing is. So first of all, quick rundown of who I am. As you might have gathered from that little discussion, I'm an amateur radio operator, electronics geek, maker. My day job is in software engineering, but in my spare time, I find weird things in the spares and repairs section of eBay and buy them and reverse engineer them, which is how this happened. So this is a Datatrak Mark II locator. I'm not sure how many of you have actually heard of Datatrak. It's actually the location finding system that Securicore built in the 80s and 90s when they had a spate of thefts of armored cash vans. There were cases where, you know, the drivers of these vans would throw their colleague out of the van and drive off into the sunset and were never seen again. There were cases where drivers were held up with various weapons and thieves took the vans. Understandably, Securicore weren't pleased about having significant amounts of cash stolen from their vans, and including the vans in a lot of cases, finding the vans burnt out, gone, you know, no forensic evidence to work off. So they built a radio location system, as you do. This is actually built off of a marine navigation system called Decker, and there's kind of a technical enhancement on how that works. So I found this thing on eBay, bought it, and got a message from the seller saying, hey, I've got a garage full of these. Do you want any more? I couldn't say no for £20. All the units I got in that auction were, they have the LF receiver, which is built onto the main board. And they also have a UHF transmitter in most of them, but they don't have the UHF EEPROM for the radio processor. So they won't work on UHF, sadly. There's a 3-pin XLR connector on the top right of the unit, which takes power, 12 volts from the vehicle power supply, the vehicle battery, ground, and a vehicle ignition system to turn it on and off, so ignition switch. There's a 15-pin digital I/O port, which on the trackback variant connects to a vibration sensor, and in the cash van variant connects to a control panel in the vehicle cab. So you can push a button on here and it will send you a location and raise an alarm. So that's obviously from the original application. There's also two RS-232 serial ports on here. COM1 is, I would call it a debug serial port from the sheer amount of noise it sends out about its navigation process. And this turns out to be very useful later on for reverse engineering it. COM2 takes commands, request position, and responds to them. Doesn't send quite so much debug information out. But it is all very, very helpful. It runs on a 68,000 processor. Amiga fans and Atari ST fans will recognize that thing. It's actually the 68HC 000, which is the low power CMOS variant that Hitachi did. It runs at 10 megahertz. The actual main clock oscillator in the thing is 20 megahertz. It's a temperature compensated crystal oscillator. That goes into a custom low frequency radio receiver, long wave radio receiver and glue ASIC, which is the little chip you can see on the bottom right there. It's 128K of RAM on the highest spec variant. Some have less. Some of that memory is battery backed with a 3-volt lithium battery and a Dallas Semiconductor NVRAM controller. And curiously enough, the firmware is actually contained on a card which plugs into the front of the receiver. I'll just flip back for a second. If you see where it says Datatrak on the front of there with 2 screws, that's actually a removable panel which reveals the EEPROM card. So you can pull out the 68K firmware and replace that without having to dismantle the unit. There's a second microprocessor, which is an Intel 8031. It's actually an 8051 without the internal ROM. That runs at 12 megahertz and has 8K of RAM and a 8 kilobyte EEPROM. That controls the UHF radio and talks to the 68000 over an 8-bit parallel interface. So there's a 8-bit latch that the 68K can write to, that the 8051 can read from, and in reverse order there's a port where the 8051 can write and the 68K can read, and there's an interrupt whenever one transmits to the other over that port. There's a dual UART chip, a 4 kilobit serial EEPROM, so 512 bytes, configured as 16-bit words, which stores the unit's serial number, UHF slot allocation, and unique ID. So when these are set up and installed in the vehicle, they're given a unique ID, which sets which slots it transmits in and which IDs it will respond to when messages are sent to it. Curiously, it runs a custom-written real-time operating system that, from what I can gather, was built from the ground up. It has thread support, mutexes, message queues, and I still haven't reverse engineered the whole thing, so it probably has more secrets. On top of that, the interface is loosely POSIX-based, and it has support for character devices, which you access by fopen, and you refer to them by name. It's kind of weird in that regard. It's quite perhaps a little bit OS 9-ish, a little bit perhaps a little bit over-engineered if I'm being brutal, but it gets the job done. It's time deterministic. Everything is locked off a 1 kilohertz, 1 millisecond tick, which comes from the radio receiver chip. So it gets a periodic interrupts and everything is timed off that. That also synchronizes to the radio signal that comes in. It's a pretty unique piece of equipment. So I spent a while reverse engineering the firmware in Ghidra with limited success. I figured out the task table formats, how to identify the different tasks that are running on the thing. I tried to write an emulator, but there's obviously something I'm missing about the real hardware, because it starts running the boot up self-check, tries to initialize the RTOS, and then promptly crashes. So it's not quite feature complete. So the next thing I did was built this little purple card at the bottom there, which is an EEPROM emulator. So there's a 5 volt to 3 volt level translation interface on the left side next to the port that plugs into the EEPROM socket. U4 is an SRAM, so a static RAM chip, and the chip on the right hand side there is a Xilinx FPGA, sorry, not an FPGA, CPLD. That's the XC95144, 144 macro cells and a lot of I/O pins, and frankly the I/O pins are what matters here. On the far right of the board you have an FTDI FT245, which talks to the Xilinx chip, and then a USB port and a couple of LEDs. JTAG port on the bottom, of course. And the Xilinx chip essentially runs a state machine that receives commands from the FT245 across the USB port. If you've seen how the Altera, the USB blaster works, it's a similar concept, similar idea. And the board that you can see on the top there is a Datatrak locator board. You can see the empty EEPROM socket on the bottom right there, which would normally have the radio EEPROM in there. There are a bunch of transition adapters. So those are a Hewlett-Packard part that comes with the 16700A logic analyzer. And then the little board, you can see between those transition adapters and the Datatrak board is a 68000 probe adapter that I designed in KiCad. So there's a socket soldered onto the top of the 68000. So 64 pins in total. This then plugs into the that socket and monitors all the, it gives access to all the pins that the 68000 has. So you can access the whole address bus, the whole data bus, and some of the control pins, which will allow you to monitor the execution of instructions, the data, the instruction codes that the 68000 is seeing on the bus, because it doesn't prefetch in any meaningful fashion. This is more or less what it's executing in the order it's executing it. So you can do cool things like telling the logic analyzer to record which addresses were executed, or which addresses opcode fetched happened from, store that, import that into Ghidra to set code addresses and instruction references, which helps a lot with the reverse engineering. I also had a dead board, which I sacrificed, removed all the components, sanded and scanned for 4 different layers of the PCB, and I'm now in the process of reverse engineering that. That freed up one of the ASIC chips. So a friend of mine happens to have in his garage the equipment necessary to decap chips, and offered to decap the chip for me and take photos. So on the right hand side you can see what amounts to a sea of gates. It's a Texas Instruments gate array chip. It's 2 metal layers, which you can see from the close up on the right hand side. And it's just an array of gate array cells, power, ground, and a couple of transistors. It's a little bit of a pain to reverse engineer given the number of gates, but it's an option for later on if there are things that we can't figure out from the firmware. It's a little bit about the network. So I mentioned earlier it's a land-based navigation network. It was initially deployed in the UK. It later expanded certainly to Malta, Austria, and the Netherlands. It uses 2 long-wave radio channels, 500 kilohertz wide. Sorry, 500 hertz wide. So very narrow band. The signal is phase modulated on top of that, but the navigation slots are frequency modulated. There are 2 frequencies it transmits inside that 500 hertz channel, which it uses for coarse positioning. There are cycles, so transmit slots, which are 1.68 seconds wide, which is 1 complete clock, timing signal, and the various nav slots, data from the transmitters to each other, and data from the transmitters to the nav receivers. That repeats every 64 cycles, which gives you a 108-second timing sequence overall, which is what is referred to in the documentation that snuck onto the Austrian radio regulator's website, is referred to as a minute, or a Datatrak minute. The transmission hasn't existed since 2011. I did a bit of Google Maps spelunking to kind of look around and figure out if any of these transmitters still exist. A few do, physically at least, but a lot of the equipment was torn out, sadly, and was probably scrapped off. There are very few known recordings of the signal, but it did make its way into a film called 144 kilohertz, which is recorded, the existence of which is recorded on the BFI's website, British Film Industry's website, and there is a copy of it on YouTube. People were listening to this signal late at night, and it has quite a mesmerizing sound, and quite a unique sound, almost like it sounds a little bit like PSK 31 or JT 65 due to the phase modulation. It's an odd little thing. Thankfully, the Locator has a ton of debug commands, and the ones I received still had good 3-volt batteries and had the serial port enabled. So I typed help on the serial port, and it very helpfully told me which commands it recognized. One of them tells you the locations of the transmitters in Ordnance Survey National Grid Easting and Northing. So I told it to tell me that information and wrote that down. So it has 24 different transmitter locations it can record. And secondary to that, it also knows the slot master and slave relationships and which transmitters are transmitting them. So to put that in perspective, it knows where the transmitters are, and it knows which of the time-divided slots they're transmitting in. So from that information, you can figure out a location map of all the transmitters, and you can see that on the right there. Huntingdon is actually the slot 1 master. So there are 2 chains. Huntingdon transmits slot 1, but also transmits the timing information for the whole of chain 1. Around about the Midlands, it would switch to chain 2. The receiver realizes it's crossing that line and switches to using Cumbria as the chain master, which is on the 144 megahertz chain. And again, Greenock, Alnwick, Stonehaven, and Asserby are all receiving the signal from Cumbria and mirroring that to allow the receivers to navigate. So the way this works is you have, as I mentioned earlier, the chains. You have one at about 130 kilohertz and another at about 140. Cumbria generates the trigger and clock timing signals for chain 2. Huntingdon does the same for chain 1 at 130 kilohertz. The slave transmitters receive the trigger and clock and synchronize to that, and then proceed to listen to and mirror the phase that they receive from the master that they're listening to, and then retransmit it. So that's called phase mirroring. And what that gives you is the same thing it gives you in the G. Sorry, I've forgotten the name of the thing. Deca and similar hyperbolic navigation systems. So you have between the transmitters, you have a straight line, which is the line of position. The baseline. And the little curved lines are the hyperbolic lines of position. So what you can see there is that they repeat roughly every half wave. So about every, I forget what the distance actually is on the high frequency version of this. The slots in there, normally you have 9 slots, but because this is time division signal, there's a second step above that called interlacing, which means you have effectively 2 of the 1.68 slots chained together. And in the first one, you transmit slots 1 to 8 and 9 to 16. And then in the second block, you have 1 to 8 and 17 to 24. So you have an actual navigation cycle time about 4 seconds. And you just measure the receiver measures the phase of the signal coming in against its internal 20 megahertz clock, does the same for the various signals in the slots, and then figures out the phase between the master station and a slave station using that information. So it has, for every cycle, 24 measurements that it's taken, but it subtracts A from B and gets what is effectively its location or its position along one of those LOPs along the baselines. So it can figure out roughly where it is. The problem is, because those repeat so often, it's very hard to go from not knowing where you are to knowing which of those you're sat on. So there's a second coarse navigation signal, which exploits the fact that if you subtract a phase measurement taken at an 80 hertz distance within a channel, effectively mix it down to baseband, mix it down to 0, and eliminate the 133 kilohertz from the equation, you get a much longer line of position repeat, which is somewhere in the region of thousands of kilometers. So it's you go from this narrow position, this fine position, to a coarse position, which allows you to figure out your position in the UK at a much coarser resolution, and then you go from that and apply the narrow position to the narrow LOPs to figure out your narrowest, so a high accuracy position down to about 30 meters. So that's what I figured out so far. I got in touch with a PhD student a while ago who did a thesis on this system and very kindly provided some details on how he'd done that, which explained a lot about what I've just explained there about the nav signal format. I built a signal generator using one of the little analog devices, DDS chips, and started feeding the clock and timing signals that his PhD explained into the receiver, and watched how the debug messages changed, and eventually got to a point where I could generate in conjunction with the reverse engineered stuff, I could generate a 64 cycle signal, which it would lock to and then complain that the clock data wasn't valid. So it had a valid trigger, but no valid clock. Sometime last year, I found on Google a copy of the network access spec, but this has been heavily redacted. So the low frequency signal has been redacted for security. There's a lot of information in there about what the navigation receivers actually transmit when they're told to, when an alarm is triggered. So there's a bit about the UHF network that sits underneath this. So there's more reverse engineering still to do. I've kind of gone back to the beginning a little bit on this and started over because some of my initial assumptions weren't right. I would very much like to speak to anyone who worked on this or who knows anything else about it. In the last couple of weeks, I've had a recording of the signal that was taken off an SDR receiver about 15 years ago that I'm currently working on and trying to decode. The eventual goal with this is to have a little box I can sit on my desk that will pretend to be the Datatrak navigation chain well enough that the receiver will lock to it and display a completely faked position. So this is something I've been working on for probably about 6 or 7 years at this point, probably longer, since I picked those units up on eBay. So that's the end of that. Perhaps a little bit whistle stop trying to keep me in the 25 minutes. So I think we'll nip into one of the breakout rooms after this, and we'll have a little chat and you can ask me questions. I'm sure you've got quite a few. So thanks for hanging around. Thanks for listening.